One of the notable hallmarks of World War I was the introduction of modern technology into warfare. Such technology as radio communications, airplanes, tanks, motorized vehicles, and high explosives are still present on the battlefield today. However, there is one weapon from World War I that has been synonymous with the conflict, and yet has rarely been used in modern warfare. In this video, I'll be talking about the dark science of mustard gas. The first year of fighting in 1914 proved to be a challenge. Intense nationalism, rapid advancement in technology, and the prolonged stalemate of trench warfare drove both sides to seek any advantage they could get. Victory was achieved by advancing and taking as much land from the enemy as possible. Different strategies were used to break the stalemate. Planes were used to bomb trenches overhead, and mines were dug below enemy trench lines, filled with explosives and then detonated. However, these strategies had shortfalls. Trenches were quickly dug in zigzag formations to prevent consistent aerial bombing, and underground mines were hazardous, sometimes resulting in cave-ins costing men and resources. One solution that was cost-effective and simple to execute was launching artillery shells filled with toxic chemicals into enemy lines. The idea was deployment of chemical weapons into enemy trenches would cause troops to disperse, and thereby weaken defenses, or they would stay and die from exposure. In either case, using chemical warfare seemed like the most effective way to break stalemate. The Germans were the first to explore the new field of chemical warfare, and employed none other than renowned chemist Fritz Haber to head the chemical warfare program. Haber first relied on chlorine gas as a chemical weapon. On the night of April 22, 1915, in Ypres, Belgium, German forces placed 6,000 steel canisters of chlorine gas along their trench lines. German meteorologists tracked wind patterns of the region and knew when to release the gaseous chlorine. Within 10 minutes, 160 tons of chlorine gas was carried into British, French, and Canadian trenches, killing thousands. Chlorine is a diatomic gas, about 2 times denser than air, pale green in color, and has an odor described as a mix of pineapple and pepper. Upon inhalation, it reacts with water in the lungs to form hydrochloric acid, resulting in horrific chemical burns to the lungs leading to suffocation. However, despite its lethality, chlorine's use was short-lived. Its green haze made it easy to see, and due to its solubility in water, soldiers could protect their airways with a rag soaked in water, or use a gas mask. Additionally, being a gas, chlorine was carried by unexpected wind patterns, causing it to disperse too quickly or be carried back to friendly trenches, as happened with the British at the Battle of Loos. The next choice for Fritz Haber was phosgene gas. Phosgene is composed of 2 chlorine atoms bound to a carbonyl group. Unlike chlorine, phosgene has no color and smells of musty hay. When inhaled, phosgene disrupts function of proteins in air sacs called alveoli in the lungs. This malfunction of proteins cause breakdown of respiratory lining, leading to pulmonary edema or fluid buildup. So much fluid accumulates in the lungs that soldiers actually drowned in their own blood. Symptoms of phosgene gas poisoning included shortness of breath, vomiting, and violent coughing accompanied by heaving up a mixture of pink and red sputum from broken down lung tissue. However, due to delayed protein reactions, effects took about 48 hours to manifest. This was not an ideal weapon as it took too long to incapacitate the enemy, and soldiers simply countered phosgene with gas masks as they had done with chlorine. After several attempts in finding the ideal chemical weapon, Fritz Haber finally settled on mustard gas. There were actually 2 different types of mustard gas being used during World War I, a species containing nitrogen and a species containing sulfur, duly named nitrogen mustards and sulfur mustards. In sulfur mustards, a sulfur atom sits in the center of the molecule, flanked by 2 carbon chains and 2 chlorine atoms. In nitrogen mustards, a nitrogen atom is positioned in the middle, attached to 3 carbon chains and 3 chlorine atoms. In its pure state, mustard gas is a clear, oily liquid with no color or smell. However, when formulated for warfare, it takes on a yellow appearance and smells similar to horseradish mustard. Mustard gas was preferred over chlorine and phosgene gas because it existed as a liquid with low volatility. It was unaffected by wind and not easily identified. Additionally, unlike phosgene and chlorine gas, which relied on inhalation as a mechanism of injury, mustard gas only had to make contact with the skin. It was deployed via artillery shells containing glass bottles. Upon detonation, the glass bottle exploded, releasing a large radius of raining mustard gas. In its mechanism of injury, mustard gas is highly lipophilic, meaning it dissolves well into substances high in fat. Human skin has a fair amount of fat composition in the hypodermis layer, making absorption of mustard gas very easy. Once beneath the skin, about 90% of it is carried away by the bloodstream, and 10% stays fixed in the local deposits. What's most insidious of this process is it goes mostly unnoticed. It's falsely believed that mustard gas acted similar to acid, and that once it touched the skin, there were immediate burns. This is not true. Mustard gas dissolving into the skin has very mild irritation and can go unnoticed. The actual damage is done by its carcinogenic properties when it damages DNA. However, this DNA damage takes several hours to occur, leaving the victim clueless to the ensuing horror. Different mustard gases affect DNA in different ways. Nitrogen-based mustard squeezes in between the two strands of the DNA helix and cross-links DNA nucleotides together by bonding to nitrogen atoms on guanine nucleotides. Once in the body, sulfur-based mustard gases form an unstable cyclic intermediate, called an ethylene episulfinium ion. In this molecule, the sulfur atom is positively charged and seeks to bind with anything that is negatively charged. Consequently, it also binds to the negatively charged nitrogen atom on guanine nucleotides in DNA. In both cases of nitrogen and sulfur-based mustard gas, the structure of DNA is altered. Cells are very receptive to changes in DNA and interprets the change in structure as DNA damage. To prevent damaged DNA from being replicated, cells undergo apoptosis or programmed cell death. This causes the classic appearance of pus-filled blisters and necrotic tissue associated with mustard gas exposure. Additionally, this alteration in DNA often leads to complications and cancer later in life. For example, a 2003 study from the Journal of Occupational and Environmental Medicine found that 34,000 veterans who were exposed to sulfur mustard used extensively during the Iran-Iraq War in the 1980s suffered numerous health complications later in life. 42% had pulmonary complications, 39% ocular complications, and 24% had skin-related complications. In a historical note regarding mustard gas, since it existed in a liquid state, soldiers often had eye-related injuries from getting splashed when shells detonated nearby, often causing temporary or permanent blindness. This very occurrence happened to a young lance corporal in the German army named Adolf Hitler. Hitler was temporarily blinded by mustard gas during the Battle of Ypres in 1918 and took 2 weeks to fully recover. Despite its horrific effects, the mortality rate from mustard gas injury during the First World War was just between 2 and 3%. Its effectiveness was not in killing the enemy, but rather the psychological trauma it instilled. Soldiers may think twice about running through no man's land that was soaked with what could be mustard gas. One could walk through a field of mustard gas and not have any signs of injury until several hours later. Soldiers were even known to retreat when it was deployed on the battlefield, playing into its psychological effects. To add to the terror, most countermeasures against mustard gas were ineffective. Gas masks did little to help, as mustard gas did most damage with contact on skin or clothing. Being a liquid, it pooled in trenches, foxholes, and contaminated groundwater. It had a higher density than water and often sank to the bottom of puddles, making it almost impossible to detect in a rain-soaked field. Despite wearing layers of clothing, it penetrated cloth, wool, and even leather. Troops became paranoid of liquids pooling in trenches and sleeping quarters. Some were hesitant to drink water sourced from a well, as mustard gas often leached into the ground. The goal of mustard gas was not death, but mental and physical incapacitation, and it worked extremely well. After the end of World War I, nearly all sides opposed future use of chemical warfare due to its inhumane effects. In 1925, the Geneva Protocol prohibited the use of all chemical weapons, as they caused unneeded suffering and often contributed to civilian deaths. Despite international opposition, mustard gas would be used during the Iran-Iraq War of 1980 to 1988 and the Syrian Civil War in 2012. In both instances, horrific injuries occurred largely in civilian populations. Chemical warfare is an act that is unanimously opposed by all nations, but unfortunately is still used in some regions of the world. Despite its horrors, it is something that humanity will forever be threatened by. Sometimes science can be seen as difficult, foreign, and even boring. Yet, there are times when science grabs our attention and draws us in, yearning for more answers. Often, what draws us in are topics that are dark, macabre, or terrifying. It's with the intention of this video that you too were drawn in and sought to have your questions answered. Thanks for watching Dark Science.